In this lesson, we will just continue solving separable differential equations, so differential equations that are written implicitly with x's and y's on each side. So we'll just keep practicing with some different algebraic techniques that are available to you for finding these general solutions. So let's just start with a handful here. So we have x squared plus 3y dy dx is equal to 0. So we want to go ahead and find the general solution. So we want to continue isolating the dy dx, or the y prime, just like we have in previous lessons. So we go ahead and we subtract the x squared to the other side. All right, so since we have dy in the numerator here, and we want to keep this as a product of a function of y with dy, we want to bring x over to the other side. So we'll keep 3y here dy, and then multiply over the dx. Now we want to take the antiderivative of each side. So 3 halves y squared, and then negative 1/3 x cubed plus c. All right, so if we want to go ahead and solve for y equals, we multiply both sides by 2/3. So negative 2/9 x cubed. This is not the same constant because I multiplied both sides by 2/3, but it is still just a constant, so I'm just going to leave it as plus c. So y is going to equal plus or minus negative 2/9 x cubed plus c. We want to leave the plus or minus in there because if they give us a point to find the particular solution, we'll choose either plus or minus on the radical here. But for now, we do need to leave that as is because it is referring to both until we know any other information. All right, so if we look at the next one, I have a y prime. You may be more comfortable writing this as a dy dx to help you separate with your variables. All right, so I want to leave y on this side, so dy stays. Sine of x is an x function, so I want to bring it over to the other side, so I divide both sides by sine of x. All right, so this requires a u substitution on the x side, your u being sine of x, and your du being cosine. So it does turn into 1 over u on that side. All right, so if I integrate just dy, I end up getting y equals, then I'm going to have natural log the absolute value of sine of x plus c. All right, so this one here is just a little more complicated. So I want to isolate the y prime. So I'm going to leave this over here. So I'm going to turn this into a dy. Then I'm going to multiply the dx over to the other side. So it looks like the only x that I really need to move over is this one, so I would divide both sides by x. So I just end up with a 2 dx. This was supposed to be a dx here, so let's fix that here real quick. So this was supposed to be 2 dx, so then I'm going to have 2 over x dx. All right, so it looks like on the y side this time I'm going to have a u sub. So my u is my denominator, so e to the y plus 1. The derivative of that is e to the y dy, which I have. So it's a 1 over u du. So the y side I'll integrate to natural log of e to the y plus 1. And then 2 natural log of x, absolute value of x plus c. All right, if we want to clean this up and solve for y equals, I do need to do a base e to both sides. These don't cancel because of the plus that's on the inside here. So if I do an exponential base e to both sides, I have e to the y plus 1 is equal to c, c e to the 2 natural log of absolute value of x. If I want to be able to cancel the e and the natural log on this side, I need to use log properties to make that an x squared. So if I think of that as a natural log of x squared, then the e and the natural log of x will cancel out. So this side here would simplify to cx squared. So I subtract the 1 over. And then if I natural log both sides, I do end up with the natural log of cx squared minus 1, just like that. So that involved a little bit more simplifying than some of the other ones. All right, so moving on to the next one here. So I want to keep y's over here with my dy, so I end up dividing over the y. I'm going to leave the x over here, and then I need to figure out how to get rid of that, so I divide over the x squared plus 4. On this one, the x side is going to have a small u sub, so x squared plus 4. So 2x dx. Well, we don't have the 2, so we need to compensate for that. Oops, there's not a negative there, pardon me. So this is a 1/2 1 over u problem. So when I integrate this side, I have natural log of absolute value of y. And I'm going to have 1/2 natural log of absolute value of x squared plus 4 plus c. All right, well, for simplifying purposes, I know that I'm going to do base e to each side, but I can't cancel this natural log here with this 1/2, so I'm going to use my log properties before I do e to both sides and make this into the natural log of the square root of x squared plus 4. I don't need to worry about the absolute value sign because anything squared plus 4 is always going to be positive. So now when I do each side with base e, those end up canceling, and then I'm going to, the c is going to be multiplied out front, and then it's going to be square root of x squared plus 4. All right, so here's just another use for a differential equation. So don't forget some of the other concepts that we've looked at before. It says find the equation of the line that passes through the point 8, 2 and has the slope y prime equals negative 9x divided by 16y. So remember, the definition of a derivative gives us the slope of a tangent line at a point to the function. So if we need to find the equation of a tangent line, we have a point and we have a means to find the slope of that line. So if I want to find the derivative at 8, 2, I can plug that in for x and y. So I end up with negative 72 over 32, which ends up reducing to negative 9/4. Okay, so the equation of the line would be y minus 2, negative 9/4 x minus 8. Okay, so differential equations can be useful again in that way, just as a quick reminder on that. Okay, so it doesn't need to necessarily always be dy's and dx's. Perhaps you have something like this question where you have du and dv. So it says find the particular solution that satisfies the initial condition. Du dv is equal to uv sine of v squared, and u of 0 is equal to 1. All right, so I'm going to keep du's on this side. I'm going to have dv's over here. I can tell that from the notation here, du being in the numerator. So I multiplied dv to the other side. So if I need to bring over the u's, I would divide by u. I'm going to leave v sine of v squared over here. Okay, so the v side this time is going to have a small substitution. Okay, I have the v, but I don't have the 2, so it is going to be a 1/2. All right, so on this side, I want to integrate the du over u, so natural log the absolute value of u. Then the integral of sine is negative cosine, so negative 1/2 cosine of v squared plus c. All right, so if I e both sides, so u equals c e to the negative 1/2 cosine of v squared. All right, so then now I want to find the particular solution. So I know that this contains the ordered pair u of 0 is equal to 1, so 1's my output, so I'm going to put that in for u here. And then I'm going to put an input of 0. So cosine of 0 is 1. So I'm going to have e to the negative 1/2 right there. So then c would equal 1 divided by e to the negative 1/2, which would reduce to e to the 1/2. You could write that as a decimal. Leaving it exactly just makes it a little bit easier. So when everything's said and done, I end up with u equals e to the 1/2 times e to the negative 1/2 cosine of v squared. And if you had wanted to clean this up a little bit, you're welcome to leave it that way, but I guess it would look a little bit prettier as e to the 1/2 minus 1/2 cosine of v squared. All right. So here's an example of a slope field. It says to sketch on the slope field two particular solutions to the differential equation that passes through these points. So if I go to the point 2, 5, notice that you see that there's these horizontal tangents here. So that's going to follow along there just like that. If I have one going through negative 3, 2, this particular solution would follow like that. So just to kind of practice sketching on slope fields and to not have the function pass through horizontal asymptote barriers like that. So which types of functions do these appear to be? So to me these look like some kind of translated exponential function. So perhaps there's some form of e to the x, like this one here, you can tell has some kind of a reflection, but they appear exponential. So if the differential equation being represented in the slope field is dy dx is equal to 4 minus y, let's actually find those two particular solutions. So let's go ahead and find the general solution first. So I'm going to leave y's on this side, so I'm going to divide the 4 minus y over as one chunk to keep it in a proper form for integrating. So there's a 1 here left as a placeholder, then I multiply by dx. So there is a small u sub here with this y. Negative 1 dy. So when you integrate, it is a 1 over u problem, but it's going to be negative natural log of 4 minus y. Is equal to x plus c. So in order to solve for y equals, I need to get rid of this negative so I can do an inverse operation with the natural log. So negative x, and again I can just keep it still as plus c. All right, so if I want to e both sides, so c e to the negative x. Okay, if I want to get y by itself, I'm going to add y to the other side and then subtract c e to the negative x. All right, so now I have a general solution. So I need to find the particular solution that passes through the point 2, 5. So I go ahead and plug in 2 for x and 5 for y. 5 minus 4 is 1. So So c is going to equal negative 1 over e to the negative 2, which would just be e squared. So getting my particular solution plugged in here, I'd have y equals 4 minus e squared e to the negative x, which would clean up to be e to the 2 minus x in exact form. If you chose to find e squared as a decimal to at least 3 decimal places, that would be fine as well, but this would be considered a more exact answer. All right, as long as you had something mathematically equivalent, that would be fine. So what about the particular solution that passes through negative 3, 2? So let's go ahead and do that. It's going to be a real similar process here. So I'm going to go ahead and plug in the opposite of my x, which would be a positive 3, is equal to 2. So I subtract over the 4, so I end up with negative 2. So c would equal 2 divided by e cubed. So if we go ahead and plug that in, so 2 divided by e cubed times e to the negative x. Probably maybe the nicest way to write this is to get rid of this negative exponent here, and then maybe make it e to the 3 minus x. I guess that probably looks the neatest. But again, as long as you have something mathematically equivalent, that's just fine. So in this lesson, we just continued practicing separating differential equations and taking the antiderivative of each side, and practice sketching on some solutions on slope fields and just doing a quick review of other applications of differential equations as well.